Hello ladies and gentlemen, today we're going to do a stoichiometry. So stoichiometry will look at these subtopics, like we'll look at the calculations, we'll look at the abundance, relative, how to calculate the relative atomic mass, how to calculate moles of molecule, how to calculate the uh, empirical formula, molecular formula, and percentage yield. Right, so that's what we are going to look at today. So stoichiometry is just is the study of quantities of materials consumed and produced in a chemical reaction. So stoichiometry, the study of quantities and quantities of materials and quantities of materials consumed uh, and produced in a chemical reaction. So this, you see, is the consumption of materials and the materials which has been produced. So that's the stoichiometry. In this, the stoichiometry is just the study of reactions. So the study of reactions, which will look at how do reactions occur, how fast do they proceed, what intermediate products, if any, are used, how much of the reactants react. You may write this: how do reactions occur, how fast do they proceed, what intermediate products, if any, are used, how much of the reactant reacts. Right, so here we say counting by weighing. So counting by weighing is said by, for example, you have 500 sweets. You have 500 sweets. Now you want to know the mass of all the sweets you have, like 500 sweets. So what you do is you can weigh 10 sweets out of 100. Then if you weigh the 10 sweets out of 100, you've given the mass of 105. 10 sweets, you've given the mass of 105 grams. So now you have to determine how much do one sweet weigh. So you divide by 10. These are 10 sweets. So if you divide by 10 sweets, what you get is if you punch a calculator, 105 divided by 10, you just get a 10.5. So which means one sweet weighs 10.5 grams. Now you want to know the mass of 500 sweets. So what you do is you write your 500 sweets, 500 sweets. These are sweets, not grams. So sweets, I just put S, sweets, multiplied by 10.5 grams over sweets. This sweet is it means one sweet. So if you multiply this one, 500 times 10.5 is just giving you 5,250. So which means your sweets, 500 sweets are weighing 250, 5,250 grams. So this is the same things you can do to the elements or given molecules when you have given a mass of an element, or element or compound in a reaction, and you have told to find the other mass of you have told to find the mass of the other compounds in the same element. You can, in the same reaction, you can use the same procedure and find the masses as required. Now, here using atomic mass to count atoms. So here we're talking about isotopes. 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 So here, grams are too large to use to measure atom. So we use atomic masses, atomic mass unit. Gram is, an atom is too small, so we can't use even gram is too big to weigh the mass of an atom. So we use atomic mass. We use atomic mass unit, which is AMU. This is what we use to measure the weight of an atom. So this one is 1 AMU. 1 AMU is equal to 1.66 exponent negative 24 grams. Is equivalent to that. So this is one atomic mass unit is equal to 1.66 exponent negative 24 grams. You have to master this. You have to know this one. Right. So we come to atomic masses. Atomic mass. Atomic mass. One atomic mass unit is 1/12. 1/12. 1/12 the mass of carbon-12 atom, which is equivalent to 1.66 exponent to negative 24. This is used to pure carbon, which is it says 1 AMU, 1 atomic mass unit is 1/12. 1 AMU is 1/12. 12th 1/12 like that. 1/12 the mass of a carbon 12 atom, which is equivalent to 1.66 exponent 24. Right. So the decimal numbers on the periodic table are atomic masses in AMU. So those are the decimal numbers. For example, we have this is nitrogen 14.007. So this, say, this is the mass of nitrogen. So this is these decimal places here. These decimal places, their atomic masses. The atomic masses in AMU. Yes, the atomic masses in AMU. So, you may raise sometimes you may raise a question like, say, why are atomic numbers not the whole numbers? So why atomic numbers are not the whole numbers? It's because they are based on the averages of atomic atoms and of isotopes. They're based on the averages of the atoms and isotopes. So that is why are not whole numbers. Right. So like we can figure out the average atomic mass from the mass of the atoms isotopes and their relative abundance. So when you are given the mass of an isotope and the relative abundance, we can figure out the average atomic mass of an element. Just simply add up by just adding up the percent as decimals times the masses of the isotope. So what it means is this is the formula for the isotope. So if you have a relative atomic mass of say R AM RAM is equal to, so they're saying you add a percent as decimals times masses of the isotope. So the percentage is the abundance percent. So say AP abundance percent over 100 over 100. Then multiply by mass, the given mass. This is the formula for the relative atomic masses. So you can add the same plus the same this, because you'll be given maybe 2, 3 isotopes. You need to find the average relative mass. So you add them, like you make this, make the other this one, add, like that. Right. So here is an example for relative for the anisotope, calculating the average mass of the chlorine. Is it chlorine? Chlorine, yes. So here is an example right here down here, what is the relative atomic mass for chlorine given that? So we have given a 75% of chlorine atoms are chlorine 35 and 0.4%, 24.5% chlorine 37. So this is the question. I think you can see here. Yeah, this one. That's the question. So let's try to calculate this one. So we have given the percent of chlorine like 75.5% of chlorine 35 and 24.5% of chlorine 37. Yeah, so we have these two things here, two isotopes of chlorine. So what we do here, we are using the same formula. So I'll just plug in. So say my relative average atomic mass in RAM. I use the RAM. AP is 75%. So I'll write that 75%. I'll divide it by 100. So I'll write my 0.755 multiplied by 35 as the mass plus is 0.245 write it here plus 0.245 multiplied by you're multiplying by 37. So when you punch on calculator, 0.755 multiplied by 35 is 26.425. I can advise you, like you have in chemistry, you shouldn't have you shouldn't do a lot of a rounding off. You may end up on a wrong answer. So just write the way it is. At the end point, you can maybe round off, but first write the full answer, or in maybe on the decimal places, maybe you can write it maybe to 4 decimal places according to maybe yes, 4 decimal places. You can write it to 4 decimal places. The answer, I mean not the answer, the value before the answer. So the answer now we can round it off to the smallest, to the least decimal, or if you're adding, to the least decimal places of the values in your calculation, or when you're multiplying the least significant figures, or when you're multiplying or dividing the least significant figures. That's your answer of your calculation. The least significant figures in your calculation, the number with the least significant figures in your calculation, that is the form you are writing your answer. It has to be in that way. But when you are calculating, please avoid a rounding off, because it may give you the wrong answer. You may calculate them very well, but end up at a wrong answer because you was rounding off. So now you are multiplying 0.245 multiplied by 87, it's giving a 9.065. 0.65, then you add these 0.65 plus 26.425. So we're having a 35.49. Now let's check in our calculations. In our calculations, what we had we had two significant figures. That's the least significant figures we had. So for this one, you can just maybe leave it only at a three significant figure. So you just round it off there. So say 35.5 AMU. This is your mass, the average mass. All right, so excuse me. Here's the another example, but for this one, for this example, you can figure it out. You can calculate. Just use the same process we've done here. This is the process here. Just use this same process. Don't even change the thing. Just use the same things we've used here. You have here we have given the question says the graph on the right shows this one. This is the graph here. Shows that shows that for every 100 atoms of natural copper, 69.09 are copper 63. So you see here 69.09. This is your AP abundance percent. So you can use the same things we've done here. This is your guide here, remember, on top here. So just do that, same things, and calculate the relative atomic mass of copper. Right, here there's another example. Yeah, here we have given the answer, but we have given the question, and these are the answers here. So we need to know, we need to find what the question says. There are two isotopes of nitrogen, one with an atomic mass of 14.0031 AMU and another one with an atomic mass of 15.0001 AMU. What is the percentage percent abundance? You can say abundance percentage abundance of each. So from here, what we need to do, since we have given just the masses, we've given the masses AMUs. So we know the percent when you have given in this situation, in this scenario, when you have three isotopes, let's say for copper, that one had one isotope, two isotope, and three isotopes. These they had this one had the percent. So the way it is, this percentage, the percent, this one, 1, 2, 3, they all add. When you add them, this percent, when you add this percentage, it will give you 100%. See, so this is the this is how it is. Those like it's the same thing. Now it has been just like something had happened, they have divided, so but there's just one. So when you add those pieces, it will form a one thing. So this is the thing here. So here the trick is, for the first mentioned value, like here, we have 14.0031. So the first mentioned value, it has normally it has the biggest percentage. So how you write that one? It is say this is a nitrogen, so say N. You can write it in this way: N is equal to 14. You write what you have given, 14.0031. Check if is what I'm writing is the correct thing here. Yes, 0031. Yes, and so just put an X, and then number 2, you say N for that second one is 15.0001. Now this one, it means it multiply 14.0031 multiplied by X. This X is the percentage percent abundance, because we don't know the percent, so this is how we put X. Now to this one, second one, we know the second one is the second percentage, the second abundance, it is less than the first one. So how it for it is for it being less, we assume that we are subtracting 100 minus X. Our X is abundance, which we don't know, but we know when we add X plus X, we are having 100. This is the 100. So when we add X plus X, we're having 100% abundance. So because we don't know what is our X, so we put an X to the first one. I mentioned that the first one is it is having the biggest abundance. Hence, yeah, we put it in such a way. Now, from here, what you do to find the abundance of this one, you put it in a normal way, like the way you find there the relative atomic mass, the formula, you know it. So you just say, I'll write it in this way. So the relative atomic mass, you get what is on periodic table, which is a 14. So 14.007. We assume that we know this one. Now is equal to, so write my 14.0031x plus 15.0001. We multiply 100. Let me just avoid using 100. I'll use the decimal places. I want to use small numbers. If you don't want to use 100, you can use a 1. So when you use a 1, which means your percent will be in, the values will be found is in a decimal points. So I'll say 1 minus x close bracket. So from here you multiply what you've put there. So I'm just having a 14.0013x 0.31x plus 15.001 times 1 is just the 15.0001 into minus 15.001 times x is 15.0001 x. So we are having an x there. Zero zero one x 001x. Now from here you can see this is an equation which is equating to 14.007. So you add like terms 14x, which is 14.0031x, and 15.001x. You add these, so it will be 14.001x. Let me punch on the calculator. You can use your calculators. So 14.001 plus 15, no, it's not plus, it's minus, there's a negative there, minus 15.0001. So we just have a point in negative point 9979. Okay, I found a 997. Let me check if I've gotten the right values. Okay, so we have 3 zeros, 1 2 3, right? So I'm having a 0.997 is equal to, no, not equal to, negative 0.997x plus 15.0001 equal to 14.007. Right, from here this 15.00, you equate it to, this is 14.007. So we subtract again. So when you subtract, so say equals, say 14.007 minus 15.0001. So I'm having a negative 0.9931. Right, so from here you divide both sides to have an x. So you divide both sides by negative 0.997, 0.997 is having a 0.996. All right, let us reduce some zeros here. We reduce some zeros to 1 with the 15 with 0.00. All right, let me take you back a bit. I think when you're using a periodic table, use sometimes there are some types of periodic table you have to you'll be recommended to use. So for this one, I've used the mass for nitrogen as 14.007. So according to this question, it was giving the answer wasn't like it wasn't accurate. The answer was precise, just precise, because yeah, so the answer was precise. So kindly use the recommended periodic tables. So what we use here, instead of using 14.007, I'll use 14.01. Right, so 14.01, this is what I'll use now to subtract. So I think you was following me, so just use 14.01 instead of a 14.007. So write 14.01 is equal to, so, I don't know if we can start afresh, but no, I say you use 14.01 to equate your equation, which is 14.0031x plus 15.0001 open bracket 1 minus x. You equate to that. So when I do my calculations, we were here, I was subtracting the 14.003 minus 003x minus 15.0001. This is not in it's not ending there. We have also a plus, a 15. This is x, 15.0001 equal to 14.01. This is what I say. This one you have to use 14.01 instead of 14.007. So when I subtract this part here, you just give me, it's giving me a negative 0.997. Now when you put like terms 15.0, this is x, 15.0001, you like them to 14.01, then you subtract there, it will give you let me try to do here 14. What I mean is, you had like here we had we have plus 15.0001 equal to 14.01. So this one you equate it to here, it will become a minus, right? Yeah, so we subtract from there. So I'm having minus 0.997 x is equal to, so 14.01 minus 14.01 minus what's that, minus 15.0001 is giving me a negative 0.9901. This is a zero. My handwriting is very good. It's very bad actually. So you find the x. What is the x? So you divide both sides by 0.997. So negative 0.997. So it's giving me a x is equal to 0.99307.9. I will try to write more decimal places to get an accurate answer. So when I round it off, this one, I'll get my x to be equal to, I'll round it off to 4 decimal places, 0.9931. All right, 9931. So from here, we have found our x. So this one, we can just multiply it, just say 0.9931 multiplied by 100. It will give you a 99.31%. This is your x, your first x actually. So for the second x, if you don't want to do this, please, if you don't want to multiply, like okay, it's fine. When you multiply this one, this is your percent for the first x. We know we have to find the two percentage abundance. So for the second x, we said 1 minus x. So where there is x, I'll put my 0.9931, what we have found there. So when I subtract this one, I'll get my, say, 1 minus answer. So I just get I don't know if this is true. Let me write it again. I say 1 minus 0.9931. So I get, oh, there's a exponent there. So I get a 0.00626. So point, see, 1, 2, 3. Okay, right, 69. This is what I get, 0.0069. 1, 2, 3. 3 decimal places. So when there, you remember, is when I multiply by 100%, the 100, I'll get, I multiply by 100, I get, so my first x is equal to 99.31%, and my second x I've gotten is 0.69%. This is our so this is our what? Our percent abundance. As you can see, as we have given the answers here, these are the answers. Let's check if there's any question here. So now we are going to talk about moles. We've completed the abundance, the isotopes. So moles, the mole. The mole. What is a mole? The mole is just a number. So it's not this is not a definition, please. So mole is abbreviated as MOL. It is a number. Now the definition of a mole: it is a number equal to the number of carbon atoms in exactly 12 grams of carbon-12. It is a number equal to the number of carbon atoms in exactly 12 grams of carbon-12. So that's the definition of an atom. Not an atom, a mole. So the number is 6.022 exponent 23 and is called Avogadro's number. So that's the number they refer to is a number equal to the number of carbon atoms in exactly 12 grams of carbon-12. So it's the Avogadro's constant, which is 6.022 exponent 23. This is an Avogadro's constant. So this Avogadro's constant so any 6.022 exponent 23 of anything is a mole. Of anything is a mole. A sample of natural elements mass expressed in grams contains 1 mole of atom. So when you have a sample of a natural element, the mass is expressed in a gram. It contains 1 mole of atoms. For example, 6.022 exponent 23 atoms of carbon, each with a mass of the 12 AMU, have mass of 12 grams. Is this true? Yes, it is true. So it has the mass of 12 grams. When you have Avogadro's number of atoms of carbon, each with so we say each atom has the mass of 12 AMU. Have mass of 12 grams. So we can try to prove this. Like when you multiply Avogadro's number multiplied by 12 AMU, what you get, then you just multiply it to remember we had the number there, which the gram. Previously we said an atom is measured in atomic mass unit, which is 1 atomic mass unit is equal to 1 atomic mass unit is equal to 1.66 exponent negative 24 exponent negative Jesus exponent negative 24. So what you do there, should I use this one? It's the same one. So what you do there, you multiply Avogadro's constant multiplied by 12 AMU. Now multiply this, what you found here, with this one. You find the grams, exactly like 12 grams there. Now this makes the numbers on the periodic table the mass of the average atom. That makes the numbers of on the periodic table the mass of the average average atoms. The molar mass here molar mass, this is the mass of 1 mole. Molar mass is is the mass of 1 mole of a substance. The molar mass is the mass of 1 mole of a substance, often called molecular weight. This is what we call a mixture. To determine the molar mass of an element, determining the molar mass of an element, you get it from the periodic table, and when it is and multiply with the subscript if it's required, then you'll find the molar mass. And so this one I won't take time because to find the molar mass, let's go do something apart from this. So I will give you an example of finding the molar mass. I'll give you a calcium cobalt. Is it this cobalt? It's not cobalt, in fact. Calcium carbonate, not cobalt. So to find the molar mass is find the mass of carbon. This is so the mass of so 3 is a subscript. So the mass of oxygen is 16. You multiply by 3, and carbon is 12.01 multiplied by 1. It's just the same 12 point. And calcium is what is calcium? What is the mass of calcium? It is 40.08. So 40.08 multiplied by 1, because we don't have you have a number 1 there. That's the subscript. 40.08 multiplied by 1, you just have the same. So here you have 3 times 6 is 16 times 3, we have a 48. So 48, 12.01 40.08. So you add those ones, that is your molar mass. You add these That is your molar mass. Okay. Yeah, since you know how to find the molar mass, we do the percentage composition. Percent composition. Percent composition. Percent composition. So the percent composition, this is the percent of each element in compound of in a is the this is the percent of each element in a compound. It's the percent of each element in a compound is composed of. So to find the percentage composition of of an element in a compound, you use the so you find the molar mass of the compound, and then when you find the molar mass of the compound, you'll be asked maybe in this case we had in this case we are calculating the molar mass of calcium carbonate. So calcium carbonate. So the molar mass of this was 100.086. 96 is not 0.8076. This was the molar mass, gram per mole. Now from here, to find the percentage percent composition, you may be asked like find the percent composition of calcium in the compound of calcium carbonate. So you know the calcium is what is the molar mass of calcium is 40.08. So 40.08. So to find the percentage of calcium, we just say calcium percentage of calcium is equal to calcium molar mass over the molar mass for calcium carbonate multiplied by 100%. Then from here you found your, so which means you plug in 40, the molar mass for calcium here. So say calcium percentage composition, percent composition is 40.08 over 100.08. You can just calculate the molar mass in a good way, then you find your right answers. Because here this is not, I don't think this is the molar mass. No, yeah, it is the molar mass, exact, but there may be some errors, but it's fine. So just do actual real calculations, but this is the formula. This is how you go to find the percent composition. This is not percentage yield, but percent composition of an element in a compound. So multiply by 100%. So what you get here is 40.08 divided by 100.08. You get multiplied by 100 get a 40%. So you just get a 40%. So calcium, in the calcium carbonate, you have 40% of calcium. This is the percent composition. So to find the percent composition, let me just so you find the mass of each of element first, divide by the total mass multiplied by 100, as we've done here. This is the right thing. Then easiest if you use a mole of the compound, easiest if you use the mole of compound. So you can even use the mole to find the percentage of percent composition, and find the percent of composition of each element in. So so that's how you can find the moles, the percent composition of any element from any compound. You can use this. All right. So we are going to do the empirical formula, how to find the empirical formula. Empirical formula. Empirical formula. Now we have a lot of work to do here, but I'll just do a few examples and those critical ones. So that we have good understanding. So steps. So from percent composition, you can determine the empirical formula. From that percent composition, you can determine the empirical formula. Empirical formula shows the lowest ratio of atoms in a molecule. Always, the empirical formula shows the lowest or the least lowest ratio of atoms in a molecule. Shows the lowest ratio of atoms in a molecule. That's the empirical formula. It is based on mole ratio. Empirical formula. So steps to calculate the empirical formula. Make sure you write these steps to calculate the empirical formula. So one, you assume a 100-gram sample of the compound so that the given percentage can directly be converted to grams. Two, use each element's molar mass to convert the grams of each element to moles. I'm sure here you can see You can see here. All right, here it is. Here it is. So these are steps of writing empirical formulas. These are steps. So you just follow these steps and you're good to go. So let's see the examples. Let's do a few examples. I'll be skipping a lot of examples because they are just similar. So I'll be just getting one from whichever is similar. From the bunch of examples, I'll get one. And we do, and we go. Right. Excuse me. So the first example I show, you can see this is right. What is it? Note 6, yes. Right. So the first example, assume the compound is 100 gram and find the moles of each atom. Now these ones, let's look at examples to these ones now. Right here. Right. These are examples. Those were examples too, but I need something which is more like involving. So as you can see, determine the empirical formula of a compound which contains 38%, 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. The good part, we have the answer here, so you can go wrong, but you have to come back because this is the right answer. So you just have to know the process, how you can do that, and find the empirical yes, arrive at the right answer with the right procedure. So here I show you how to do that. So as we've been told that we have to assume that we have 100 grams of the mass and convert the percent to mass. Right. So we have given the carbon is 38.67%. So for me, this because we have told that we assume that the 100 grams, we have the 100 grams of mass, so to convert it to grams, the percent to grams. So you just what you have given, the percentage you have given, you just say 100, you put a gram instead of saying percent, then you multiply by one more. What it is here, we are finding the moles first of a carbon. So to find the moles, since we have given the mass in percent, so this is the mass. So to find the moles, I think you know how to find the moles. So to find the mole, the formula is I will write N. This is number of moles is equal to the mass over molar mass. Mister. The molar mass, I have shown you how to find the molar mass there, but this one is given. If you are not given this, maybe you might be given this one, then you can find this mass. So it's not the issue. It's not the issue, but this one is always there. Periodic table, just go there, you find the molar mass. Right. So this is the formula. So the formula, you are not, the way you do here, you use the chain reaction other than using the formula. So this is how we do chain reaction. So your molar mass of carbon is 12.01. Yes, the molar mass 12.01. So when you multiply those things, you get, what is the mole? You get so just divide 38.67 divide by 12.01, you get a 3.2198. Try by all means to write at least 4 decimal places without rounding off. You can round off when you are far from, like maybe 5 decimal 5 decimal places, you can round it off. But yeah, 3.2198. So I'm writing 4 decimal places. I need an accurate answer. So mark that. This is the mass for carbon. This is the mass for carbon. Hydrogen, not the mass, the moles for carbon. For carbon is hydrogen. We have given the percent of 16.22. So put a gram multiplied by a mole over the mass of hydrogen is 1.01, the molar mass. So 16.22 divided by 0.01, you get a 16 point. You get a 16 point. This is your mole. 0.0594, like that. I have numbers there, but I've chosen to get, because after this one there's a 0, so 0, we round it off. This is my 4 decimal places. This is just a 4. So this is the mole for hydrogen. Last but not the least, we have a nitrogen, and a nitrogen is equal to a nitrogen, we have given 45.11%, multiplied by a mole over the mass of nitrogen is 14.01. So 45.11 divided by 14.01, get a 3.21, get the same answer with the first one, 92198. Right, so we can rewrite these ones. I want you to see now: carbon, hydrogen, and nitrogen. So carbon, we have a 3.2198. Hydrogen, we have 16.22. 0.0594, and nitrogen we have 3.2198. So you see, now from here you divide your moles with the lowest number of moles. You divide everybody with the lowest number of moles. So my lowest number of moles is 3.2198. So we'll divide this one, divide that, and that one, and this one. You can use your calculators to find 98. So it's just giving me 1 here, and here 1. Let me do for that one. I use my calculator. 94 divided by 3.2198, which is a 4.98. This is not bad. We are rounding it off, so we round it off to 5. Sorry. So when we round it off, 4.9 is 4.9. We round it off, we get a 5. So I'm just writing a 5 here. 5 here. So now my empirical formula is CH5N, as required. So here we have a few things to say. I have few things to say. There are sometimes you may find the values like, but you have to be careful when you are dividing your moles, the least number of moles, when you're finding the subscript of the element, as we are dividing the moles, when you find a 0.5, I'm not saying a 0.5, this can be 8.7, 1.5, 2.5, as long as it's 0.5, a number 0.5, make sure you multiply by 2 everything what you have found, as long as you have, as long as at one point you have 1 or 2 point you have 0.5, you multiply by 2. Any subscript, every subscript, you multiply by 2. Then if you have, when you're dividing, you have found something like 6.33, I say 0.33, any value will have 0.33, just multiply that with the, not only this, multiply everything in your findings by a 3. Even if it's 0.66, multiply by 3, just multiply by 3. So 3.33 and 0.66, you multiply by 3 to find the whole number, of that, because we don't have empirical formula which we can find carbon then a subscript of a 2.5. No, it's not right. So you have to multiply that 2.5, you multiply it by a 2. So when you multiply 2.5 by 2, you get a 5, right? So but you don't multiply. So let's say I say here a carbon, hydrogen, I put my oxygen. So here I found my oxygen 0.5, then here 3, then here 1. So because I have 0.5 here, meaning I'm multiplying everybody by 2, so that I get a 2, a 6, a what is this, a 3. I'm getting the whole numbers. Now this is right. You multiply everybody with the same number according to the the type of fraction you have. If it's 0.3, you multiply by 3. If it's 0.66, you multiply by 3. 0.33, you multiply by 3. 0.5, you multiply by 2. And when you have found such, like you have a 0.25, you have a 0.25 or 0.75, such kind of numbers, you multiply by a 4. You multiply by a 4. You have to get me here. What I mean here, when even if it's a single point, I said I'm repeating. So I say my carbon is 6.25. Then here my hydrogen is 10. My oxygen is 5. So which means as long as I have 6.25, I am multiplying this everybody. This is a multiplying, it's not taking like it's wrong. No, I'm multiplying everybody by what? 4. Multiplying everybody by 4. By 4. So which means you have a 40, you need a whole number, a 20, and I don't know that one, 6.25 multiplied by 4, you get a 25. You have the whole numbers. That's the rule. Last but not the least, when you have found the a 0.2 and a 0.4 multiplied by 5. Let's multiply by 5. Yeah, these are the conditions. These are some like problems you can be facing in calculating the empirical formulas. So this was the example 1, and I've said a lot of in it. So we are going to do something here, which is empirical formula, empirical to molecular formula. We have empirical formula. Now we need to molecular formula. So the molecular formula shows the lowest. Empirical formula shows the lowest ratios as mentioned earlier. Molecular formula shows the actual molecule. We need to find the molar mass of the so from here we need to find the molar mass ratio of empirical to molar mass. We will tell you the molecular. formula. So when you find the molar mass, now we'll do the ratio. Molar mass of empirical formula. So the ratio of empirical formula to molar mass will tell you the molecular formula. The molar mass, the molar mass for empirical so here the 1 molar mass will be given, but for the empirical formula you have to calculate on your own. You find the empirical formula, then you calculate the molar mass. You find the molar mass, then you find the number, you find the ratio of finding the molar mass. So the ratio of finding them, for you to find the molar mass, molecular formula, the ratio is N is equal to molar mass over empirical formula mass. This is the molar mass for the empirical formula. This is the ratio, how you can find N. So when you find the N, your N will be written as N open, then you put empirical formula. Empirical formula. So which means the N is multiplying with what is the molecule which is here. Any element is multiplying with the N to find the molecular formula. Let's go to the example. We should not waste much of time. Let me show you how few steps here of finding empirical formula. So these are the steps and a few explanation on empirical formula. This is what I was talking about for the empirical formula, the formulas and everything needed. So here is an example. Example 1. It is solved. So let me get another good one. All right, this one. Example 2. We don't have, it's not solved, this one. So determine the empirical formula, empirical and molecular formula of a compound that gives the following percent analysis. So we have given the values there. We need to find the empirical formula and go to molecular formula. All right. So the same process of finding the molecular formula, that's what we use, and at last you can do this. So at last you use, okay, now you have given the molecular formula, this one, and the empirical formula mass you calculate on your own, but this one is always given. Let's do some showings of calculations. Right. So as the question reads, and we've given the carbon the percent of 74.65. So I'm calculating the moles direct by mole over 12.01, which is it is giving us a what? It's giving us 74.65 divided by 12.01 is giving us a 6.2 21565. This is the mole, 6.21565, the mole. And we have oh sorry, this is the second one is so this is not a carbon, it's a chlorine. We need it's a chlorine and carbon. This is the carbon now. We have a 24.27, so multiplied by one more over. So I've missed the masses here. If it's a chlorine, now is we don't need that 12.01. Here we need a 35.45 grams per mole. Now we find our 74.65 divided by 35.45, which is a 2.348. 2.34877. I'm avoiding to rounding off because we can find the wrong answers. Now carbon is 24.27 grams, 24.27 grams multiplied by one more over 12.01. For this one we find 24.27 divided by 12.01 is 2.0208. 2.0208. I hope you've gotten that one, because I'll write different things here. Let me do my calculation. So this is for carbon. This is for carbon. I think this is, I'm getting tired. The percent is not a 71 for chloride, is 7. It's not 74, it's 71. So for chloride, I think I've written I wrote wrong things here. Like I didn't get the correct gram. So it's 71.65 multiplied by a mole over then 35.45. So this one is giving us a 2.0211. This is the chloride. Then we go for carbon. Carbon is 24.27 multiplied by a mole over 12.01, and this one is giving us 4.27 divided by 12.01 is giving us a 2. This one was correct, 2.0208. Well, right. Now for hydrogen, we've given a 4.07 multiplied by a mole over 1.01. This is the mass for hydrogen. Yes. So for that one, this is 4.07 divided by 1.01, which is giving us a 4.0297. So these are our masses, and the moles. We are finding the moles. It's not the masses. These are not masses. They are moles. So I'm rewriting these ones. I start with carbon. So carbon was 2.0208. Chlorine, I'll put a hydrogen, chlorine last. Hydrogen is 4.0297, and the chlorine is 2.0211. So what is the lowest? And I said the least. The least is 2.0208. This is the least. It's the least. So 2.0208 over here 2.0208, and here we have 2.0208. What we are having is so when we divide those values, just having 1, 2, 1. These are the values we are getting. 1, 2, 1. 1, 2, 1. So the empirical formula is carbon H2 chlorine. This is the empirical formula. As you can see there, the answer, empirical formula, as you can see there. And we need to find the molecular formula. So the molecular formula, we need to find the molar mass first for the empirical. So the molar mass is 35.45, and 2 times 1.01 and 12.01. So just add these, so multiply, add, plus sunshine. So we're just getting, don't have a space, big space. So you add, you multiply first. So this one multiplied by 1, this one multiplied by 1, this one 2 multiplied by that. So then you have a 35.45, and here you have a 2.02, and here we have a 12.01. So when we add, we have 84.794. So this is our empirical formula mass. So remember the formula for the ratio of empirical to find the empirical formula is N is equal to molar mass over empirical formula mass. So what you get here is the molar mass we have given. What have we given? We've given 98 point. So say N is equal to 98.96 over our calculated empirical molar mass is 49.48. So just divide those 98.96 divided by 49.48. We have a 2. So our N is equal to 2. So what we do here, sorry. This is what I was writing, sorry. So just divide by this. This is what we are given, and this one is what we have calculated empirical formula mass, and this is molar mass. So what we found is when we divide these, we find a 2. That's the N. So from that, we are just plugging our N. This is the formula. The molar, the empirical formula is CH2 CHL. So which means I'm putting a 2 here because N is 2. So CH2Cl, you're having a C2H4 Cl2. This is your molecular formula as required. Let's take a break. So we'll continue with this video. We'll continue the empirical formula. We have a lot of questions to solve here. So let's end here, and let me show you what you can calculate on your own. Like you can calculate for because for practice here. So you can do this, you can do this one and this one. No, here. So we'll start from combustion analysis is another story there. So we start from there. We have a lot of questions on there. We have a lot of questions to do there. Combustion analysis and a lot of examples. So continue from here, but make sure you do these examples here. This one was already, we've calculated this one, so it's your job to do this one and this one right too. There. All right.